Let's begin our journey into compressions and expansions with a familiar friend, the absolute value graph, y equals the absolute value of x. This simple graph forms a V shape, with its vertex right at the origin, 0, 0. The graph rises at a 45-degree angle on both sides of the vertex, extending infinitely. Remember, the absolute value of a number is its distance from 0. Whether the number is positive or negative, its absolute value is always positive. This characteristic creates the distinctive V shape of the graph. The beauty of the absolute value graph lies in its simplicity. It serves as a perfect starting point to explore how changing the equation affects the graph's size and position. These changes are what we call transformations. Imagine grabbing the points of the absolute value graph above and below the x-axis, as if you were stretching a rubber band, and pulling them away from the x-axis, causing the graph to stretch upwards and downwards. This pulling action results in a vertical stretch, making the graph appear taller and narrower. Mathematically, we represent this change with the equation y equals a times the absolute value of x, where a is a constant that determines the degree of stretching or compressing. When a is greater than 1, the graph stretches vertically, making it appear more elongated. For instance, y equals 2 times the absolute value of x will make the graph twice as tall, effectively doubling its height. Each y-coordinate of the original graph is multiplied by 2, resulting in a significant vertical stretch. Conversely, when a is between 0 and 1, the graph undergoes vertical compression, appearing to shrink towards the x-axis, making it shorter and wider. For example, y equals 1/2 times the absolute value of x will make the graph half as tall, reducing its height by 50%. Each y-coordinate of the original graph is multiplied by 1/2, leading to a noticeable vertical compression. Now imagine pushing the sides of the absolute value graph towards the y-axis, like squeezing an accordion. This visual can help you understand how the graph changes shape. This action represents a horizontal compression, where the graph becomes narrower. We express this change using the equation y equals the absolute value of b times x, where b is a constant. This constant b determines the degree of compression or expansion. When b is greater than 1, the graph compresses horizontally, making it look more squeezed. For example, y equals the absolute value of 2 times x will make the graph appear narrower, squeezed towards the y-axis. This is because each x-coordinate is multiplied by 2. Each x-coordinate of the original graph is effectively halved to create this compression. This results in the graph being more compact. On the other hand, when b is between 0 and 1, the graph undergoes horizontal expansion or stretching. This makes the graph look wider. It appears wider as if someone pulled it away from the y-axis, stretching it out. For instance, y equals the absolute value of 1/2 times x will make the graph twice as wide. This is because each x-coordinate is multiplied by 1/2. Each x-coordinate of the original graph is doubled to create this expansion, resulting in a wider graph. Section 4. Combining transformations. Putting it all together. What happens when we combine both vertical and horizontal transformations? This is where things get really interesting. The equation becomes y equals a times the absolute value of bx. This combination allows us to manipulate the graph in multiple ways. Now both the a and b values influence the graph's shape and size. The a value affects the vertical stretch or compression, while the b value impacts the horizontal stretch or compression. Let's consider the transformation y equals 2 times the absolute value of 1/2 x. This example will help us understand the combined effect. The 2 in front of the absolute value tells us the graph is vertically stretched by a factor of 2. This means every point on the graph is pulled away from the x-axis. The 1/2 inside the absolute value indicates a horizontal expansion by a factor of 2. This means the graph is stretched away from the y-axis. The order of transformations can sometimes matter, especially when other transformations like reflections or translations are involved. It's important to follow the correct sequence. However, for simple stretches and compressions, the order in which you apply the a and b values is less critical. Understanding these principles will help you master graph transformations. Section 5. Conclusion. Mastering transformations. Understanding how to manipulate the basic equation of a graph opens up a world of possibilities. We can stretch, shrink, compress, and expand graphs in both vertical and horizontal directions. These transformations are not limited to the absolute value graph, they apply to any function. Remember the key takeaways? A controls the vertical changes, and B governs the horizontal changes. By experimenting with different values of A and B, you can gain a deeper understanding of how these transformations affect the appearance of various functions. So keep exploring and have fun transforming those graphs.